Okay, so we're moving on to inductors, and just like we did with capacitors, we're going to first look at the voltage-current relationships for inductors, and then look at the energy that's stored inside an inductor. And then we'll look at here some uses of inductors as well here. And then in the next lesson, we will do some examples using inductors. So first off, let's look at the symbol for inductors. There's two commonly used symbols. This one, just kind of some little humps here. And I'll go ahead and label this V sub L as voltage across an inductor, because we use L for the inductance, and you might say, well, why don't we use I for the inductance? And that should be pretty obvious because we use I for current, so we don't want to be mixing up things like that, so we use L for an inductance. And then, of course, there's still some current going through this inductor as well. Now, this is one common way to draw them. Another common way, and sometimes in some circuit simulators you'll see them like this, is where they really emphasize the fact that most inductors are literally just coils of wire. So it almost looks like a spring that you're drawing here, a symbol for a spring, but it's still just the same thing. Now, from my experience, I have not encountered inductors where it matters they have a polarity to it. There might be some inductors out there that are like that, but in general, inductors, it doesn't matter what way you put them into a circuit, just like resistors. So it's not like where capacitors, we have the electrolytic capacitors, and those can cause us some problems if we're not careful. All right, so then let's dive into the voltage current characteristics. Well, this uses a derivative just like the capacitor did, except in this case what we have is that the voltage across an inductor is equal to the inductance times the derivative of the current. Now, I'm not going to rewrite the table down because we're going to still use the same kinds of equations to answer questions regarding inductors. So we're not going to sit here and suddenly have a whole bunch of new derivatives. That table of derivatives that we put down, that very basic table. Let me emphasize how basic that table is. When you take calculus, you'll learn all sorts of other rules and formulas for derivatives, but that's a basic table of what we would need for the material in this course. And so if we're looking at the the voltage current relationship, we have that the voltage across the inductor is equal to L times the derivative of the current. So what we should see here is that if the current through an inductor is not changing, in other words, it is constant, then the voltage is zero. And what I mean by that, let's just suppose that here, just to kind of maybe put some real numbers here to make it a little bit easier to understand, let's suppose that we have an inductor and the current through this inductor is 3 amps. So it's constant. It's a constant 3 amps going through this inductor. Well, then from our derivative rules, we know that the derivative of a number like that is just simply 0, which then, of course, the voltage would be L times 0, which of course doesn't matter the value of the inductance. That means the voltage is equal to 0. So for a capacitor, for an inductor, that has been charged up. I don't like the word charge for inductors, but it is what we're doing here. I haven't thought of a better word to use instead of charged. But for an inductor that has been charged, it acts as a short. Now let's emphasize again here, DC only. Because if we have an AC current, an exponential or some kind of sine or cosine, those derivatives aren't zero. So that means then the voltage across the inductor is not zero. And so it's not going to be behaving as a short in those cases. So it's only for the DCs where it behaves as a short. Now, let's look at the energy stored in an inductor. The energy stored in an inductor, we'll do W omega sub L. You'll notice that this formula is going to look almost identical to another formula we had here with one change here. It is 1/2 the inductance times the current squared. So remember, for the capacitor is 1/2 capacitance times the voltage squared, where for an inductor it's 1/2 L times IL squared. So very similar formula, it's just we're using current now instead of voltage. And in your texts, and most texts go through the explanation on how to derive this. It does use some calculus in it, which is some of the reason why I've skipped some of the derivations of this formula for energy. But the derivation of this formula for energy is actually, something that most textbooks will show you if you're interested in seeing that. But really, I don't think it's that critical on the derivation of where that comes from. It's more critical that we understand how to use these formulas and how to apply them. All right. Well, let's talk now about how inductors are made. And actually, I'm going to go here. This PDF I'm going to show you in a second here. This is some of our courses that I was at, but I'm going to go to a website that I use quite a bit. Some of you might be familiar with it. If my computer loads it in here, we'll see how my network's doing here. It should be loading in. It says I have internet access. Come on. If it doesn't come up here in a second. I'm at the far end of where my wireless connection is in my house. So let's try that one more time. All right, it's not loading in, but that's fine. We'll go back to this tab here. What I was going to show you is that often inductors, if you're buying fixed value inductors, fixed value inductors are often just coils of, in most cases, they're copper wire. And the coils can be around air, sometimes they're around iron or other ferrite metals, meaning metals that can conduct a magnetic field. You won't see an inductor with a core being like aluminum, because aluminum is not a ferrite metal. So you won't see inductors being made with a core being aluminum. But you will see inductors that are just they're literally just a coil of wire, and the center of them might be air, or as I said, some iron here. So the page I had brought up here this is just something PDF I found on the internet. I can't remember exactly where I just did a Google search for it, but this is can't find inductors you need for an antenna, a tuner, or amplifier. Build your own. It's easy, and it really is easy to build your own inductors. And these are all air coil inductors, and you can see, yeah, they're literally just coils of copper wire. And I'm not going to read through this here, but then it also is showing them putting some, plastic posts here. That's really just for mounting purposes in a PC, so that it has some mounting support in a PC board. And even says that in the figure. And then it's, coil frames, like how do you actually get this? And then it also, coil and form data gets you some other things of this nature. Table 1, then the winding of the coils, it kind of shows you how to wind them. There's things called building ribs and, mounting the coil, wire sizes, and it says there's no given wire size, and as far as the gauge, your application depicts the wire size and physical needs, but here is where you can get into the approximate inductance of a single layer air coil. Can be simplified from this formula, where this is the inductance in microhenries, where you have D, which is the coil diameter in inches from wire center to wire center. So that's the actual size of the coil that you're making. N is the number of turns you've done, and then L is the coil length in inches. So that gets you, and then it gives you an example here. What is the inductance of coil if it has 48 turns, wound at 32 turns per inch, and a diameter of 3/4 inches? So then it gives you all the numbers here that you can compute, and then it gives you, okay, well, what is the inductance, and then it becomes 18 microhenries. And then you can also run the formula backwards. So it's kind of interesting. You can build your own coils. Some of you, if you've been exposed to this, you may have done this before, but it's kind of an interesting thing. You can actually build your own inductors, and not just build ones that, here's an inductor. You can build your own inductors that you could actually use in a circuit board. Now, obviously, if you're mass producing, you're not going to be sitting there making your coils by hand, and that's why I was going to digikey.com. My internet didn't work with me, but that's why I went there, because they of course have tons of coils, and I was just going to show you that, hey, yes, some of these coils are literally just copper wire wound around a core of some sort. All right, so that's how they're made, but let's talk about some uses for inductors. So they're often used as chokes, is what they're sometimes referred to, and used in what's referred to as kind of surge protection. You probably have all heard of this. I mean, we all have power strips at home that are, this is a surge protected power strip, and what does that mean? Well, it means it's protecting against surges both in current and in voltage is what it's doing. And how those work here is that if I have an inductor here, and I have some load here, and this has been on for a long time. So it's been on for a long time, so I'm going to just draw a dotted line through it. So it's behaving as a short, right? So basically what that's doing is saying, okay, well, whatever my power supply is here, and I've got some power, supply, maybe other circuitry sitting over here. I'll put a box here for other circuitry. I've got some power supply and everything connected up, and this is my load that I'm powering. Now, what happens here is that, you say, it's like, well, what happens if you get a spike of current that you don't want going through? Sometimes that can happen where you get current spikes, and that's a real phenomenon. Just think of your own power lines and things of that nature. Well, if I get a real large spike of current, so I get I spike here, well, in order for the current to change rapidly, we must have infinite voltage. And now it's not technically truly infinite. And why do we say that? Okay, well, something again you'll learn in calculus is that a derivative gives you a rate of change. How fast do you need to change the current? So let's just, for instance, say we're going to go to an extreme case here. Say we have a spike of current that's from 1 amp is what we're operating at, and we have a spike 1 amp that goes to 10 amps. So we have a 10 amp spike coming through here. Well, I want to change from 1 amp to 10 amps, and I want to do that quickly. Well, if I want to do that quickly, you can think of this as just a slope. So if I want to do 10 minus 1 amp, because I want to change it quickly, and if I want to change it quickly, let's say the time I want to change it in is over a period of, let's just say, 1 millisecond. I want to change it that fast. So if I do 9 divided by 0.001 for 1 millisecond, that means I need 9,000 volts in order to process that current change that fast. I need 9,000 volts across that inductor. But we know if it's been on for a long time, it's acting as a short. So if it's on for a long time, since on for a long time, we know that the voltage is equal to 0 volts. So in other words, it cannot change its current rapidly. It's not to say it can't change its current. Absolutely, the current can change. But if you get a spike coming through here, it won't be able to, it won't let that spike. And that's why it's sometimes referred to as a choke, as it's choking out current spikes. Now, again, if we were wanting to switch from 1 amp to 10 amp and it wasn't necessarily a spike, we're wanting to ramp it up, that's again the inductors preventing it from this load from suddenly just having a switch from 1 amp to 10 amp on it. So this prevents any kind of current spikes from going to your load. So you'll often see these in circuits, especially like towards the beginning of a circuit or coming off of a power supply or in surge protection, because they're protecting against current spikes. So that's one application of these. Another application of these is, in filter design. If any of you have ever gotten into audio, there's sometimes, if you've ever gotten into audio and done woofers and subwoofers and tweeters and all that other stuff, you've probably heard of something called a crossover network. Well, it's, that's what audio people refer to it as. It's really should be called, in my opinion, crossover filter. Because really what you're doing is you're creating filters, and what you're doing is basically you're filtering your audio such that the low frequencies go to the woofer and the high frequencies go to the tweeter. But you're making sure that you're doing it in a way so that the entire audio signal still gets played out on the speaker, so that you're not suddenly missing some frequencies in the middle of the audio signal. And often we'll use inductors in some of those crossover networks. So lots of applications for inductors. We'll go ahead and end the lesson here today, and the next lesson we'll review and put some kind of key points about our inductors down, and we'll go through some examples.